Sure.
Walk away from the speaker.
All right. I hope I'm audible. Can you see the levels? All good? Testing, testing. Check, check, check. Check, check, check. Check, check, check. Check, check, check. Check, check, check.
Gautam, you need to rally your audience to listen to the speaker. He's ready to speak.
Everyone, please take a seat. Anirudh Rauji is about to start.
We can all grab chairs from here, there.
Yeah, sure.
What's the streaming gap like?
It will be about 4 or 5 minutes, I think.
Okay,
Actually, it should be about a minute.
okay.
You have 6 people watching online right now.
Nice. Hello, 6 people watching online. Okay. Good morning, everyone. Welcome to Bengaluru Systems Meetup number 16. I am super happy to see all of you folks showing up here, and I really hope everyone has something nice that they'll take away from this meetup. Hopefully, you get inspired to speak at some other meetup, or hopefully, you get inspired to share what you've learned in systems with the community at large. So, thank you so much for showing up. I think we have 2 talks today. Yeah, 2 talks should be good. So the first one is from me. This is less of a talk. This is more unstructured exploration of a code base. So this right here is the level DB code base. This is one of the earliest open source key value stores, if I'm not wrong. This came out of Google. Yeah. So, oops. Yeah. So this came out of Google, and it is, I believe, one of the very first implementations of a log-structured merge tree or an LSM tree, which is sort of why this is interesting to me. And what I'm essentially going to do is I'm going to walk through the right code path, and we're going to sort of. So the thing is, when I started working, the task I had was that there's a really large code base that exists. That's existed for a while now, and it has its own quirks, it has its own nitty-gritties, it has its own finer details that aren't exactly easy to grasp, and especially in cases where the documentation is somewhat comprehensive, but doesn't really give you an on-the-ground look at the code, which I think is the case for a lot of really good and well-known projects as well, right? Like, for example, if you look at RocksDB. There's a lot of good documentation on what RocksDB does, what its features are, right? However, when you start exploring the code, it's a slightly different story, because then you'll realize that, hey, to get it from concept to actual working reality, there's a bunch of abstractions that have to be built around it. There's a whole bunch of maintainability stuff. There's a whole bunch of performance stuff that happens in the gap from the clean room concept to production implementation, right? So I really struggled with navigating the code base in the sense that I wanted to have a much better understanding of why it's built this way and how exactly it works. So this exploration is an effort in two things. One is to sort of be willing to look somewhat confused and befuddled in front of everyone else so that we sort of normalize that, hey, it is okay to not know everything about a new code base that you're seeing. And also to sort of share the process that I've learned in terms of how you can go about navigating a code base that you aren't exactly familiar with. And we're going to do this in 2-3 ways. So the code path specifically that I want to explore is the right code path here. And we're going to do that by going through the tests and by using the debugger so we can understand exactly what happens when we say, hey, there's a write happening in this key value database. So that's the first talk. And the second talk is going to be from Gautam, who is right here. And it is going to be about Gautam's work on full text search. So, sorry? Yes, sorry. I forgot to mention, we have a third talk as well from Kiran about... So today's live streaming setup is thanks to Hasgeek. And we have Kiran from Hasgeek right here. This is a very interesting piece of hardware that is an entirely self-contained unit for all of our live streaming and recording. And I think we'd love to hear about that as well. So we'll have Kiran as well talking about the box. Do you have a name for the box?
It's just called a video kit right now.
Okay.
Got down to branding
Okay, we'll have a nice name for the video kit coming up soon. Okay, cool. So the idea is sort of that we're just going to walk through the code here and take a look at what's really going on under the hood. So for those of you who are not familiar, LevelDB is a key value store. It's one of the earliest key value stores that were open source, basically. And the essence of using a key value store is sometimes there is data that you have to store. So coming from a traditional backend dev background, as I did, the idea of persistence is not something that you really think too much about. You usually have a database that you push your data into, which is a very sort of neat black box that you take that takes care of persisting your data. But, well, I mean, that's the beauty of computer science, right? Like, the database does a lot of heavy lifting under the hood to make sure that your data is persisted correctly. And if you have a very simple use case where it's like, hey, I have one piece of data that I need to persist, and I need to do it once or twice, then it's fairly simple. Like, you can write a file, and that's the abstraction that we're comfortable with, right? Underneath the hood, there are whole really dense, beautiful pieces of architecture in the form of the file system, in the form of the drivers, in the form of all this art that's going on underneath to make sure that this happens correctly and in a performant way. But where you start seeing the gaps is when you start entering slightly higher performance scenarios, right? So let's say, for example, that one piece of data is going to be concurrently modified by 2 clients, right? Now you have to start asking questions about, hey, how do these 2 clients synchronize with each other, right? How do I ensure that if I'm storing 2 words, how do I ensure that I'm never in a state where the first client has written the first word and the second client has written the second word, and both of them don't know that this sort of inconsistency is there, right? So we can build up the complexity layer by layer, but essentially the key value store is, I think, in a lot of ways, the foundational layer of that. So if you've used MySQL, you might have heard of InnoDB or MyISAM, or you might have heard of RocksDB, right? Which is the underlying piece of data infra for a lot of larger projects. So LevelDB, in my opinion, is one of the simplest forms of a key value store. When I say simplest, I mean code base wise, it is fairly small, thus making it an ideal subject for a pedagogical exploration of how an LSM tree is implemented and written, right? So in the previous meetup, which we don't have a recording of, but I basically did a small walkthrough of the high-level architecture. And we can probably do that today as well if it doesn't take too much time. And we can, so the target for today is that we walk through how LevelDB does writes. And we have, so the method that we're going to follow is that the level DB code base, as many good code bases do, have a lot of unit tests, right? So you can see that there is this one primitive test called the read-write test. And this while change options is a way of implementing parameterized testing that I won't exactly go into. But in essence, this is what's going on. Okay, so this is a C++ code base. How many of you are familiar with C++? And it's okay if you're not. Okay, not bad. We are in some decent luck today. So it's completely okay if you're not. I think more of the highlight here is to understand from a high-level conceptual overview what's going on. Okay. So you see that we have a put. So we're doing so key value store's job is to store keys and the associated values, right? So we're doing a put for a key that's foo and the value is v1, and then we're asserting that when we get foo, the value is v1. This is a very simple sanity test, right? But it turns out that there is a surprising amount of complexity. So this is ideally what your client or your user sees, right? This is the abstraction. This is a contract that we have. So when you say that the put has succeeded, the get has to give you that value back, okay? So let's sort of dive into how that happens. And what I'm going to do right now is I'm going to use the debugger. So this is CLine. I have a local build of level DB set up from a code base point of view, right? And I've put a debugger breakpoint here so that we can observe what's going on when we run this test. Okay, before that, do you folks want to see a very high-level architectural overview, or shall we start by exploring first? Show of hands. Who wants the high-level architecture overview? Okay, cool. Let's do that. So I believe most of what we need is here. So the C++ code base structure, like this is a fairly common structure that you have. You have an include folder, which has all these things, all these top-level header files. And we don't have to bother exactly with what all of this is. But you can see, right, that the include folder has a very, fairly small number of files. So this is a relatively simple code base to go through. You can see the copyright 2011, right? So the level DB authors. So yeah, okay. Looking at the symbols and the structure here, this is a very useful tab that I find that gives you a list of all the symbols and the high-level structure that's there. So it's essentially, it gives you the benefit of reading the whole file without doing so. It just gives you an outline of all the functions and stuff that you can see. So I'm sure this view is there in VS Code as well. This is something that you don't really see a lot when you're working on smaller scale projects, but this is a really helpful thing in slightly larger projects where the code base is less grokkable or less navigable. So I'm just gonna head to this class. Okay, so here we are. This is the high-level object that we're going to stick with. So it's a persistent ordered map from keys to values. So this is the contract that we are enforcing, persistent. You want to do it safely, you want to do it correctly. You want to ensure that the guarantee is if you've been told as a client that your data has been persisted, that data survives across restarts, across minor levels of corruption, across different other scenarios that can happen that might impact the data being present on disk. Okay, so public, this is a exposed interface. So the first function that we have is open. This essentially takes in some options, takes in the name, which I believe is the path that the event that the DB is stored at, takes a reference to a database pointer. And you can see a lot of these are virtual functions, right? So simply put, this is the contract that a database in this code base implements. This is helpful in terms of, in general, when you have an abstraction like this, it's helpful because let's say you have a slight variation that you want to run the same suite of tests on, right? So if your tests run on the contract, then your implementation can be swapped out for your benefit without having to do a full refactor. And this is not level DB specific, this is just general maintainability and hygiene that you might want to take as a design choice, okay? So that's why you'll see these virtual methods, right? So for those of you not familiar with virtual methods, this is essentially like an interface that you're defining in Go, or I believe TypeScript. I believe JS has interfaces as well. My JS is very rusty, But yeah, so the simplest analogy is like you can look at a Go interface, right? Cool. So we have the open method that does all the initialization that we need. So one interesting thing I want to highlight is this status bit. It's a class. It's not an enum or a single item. This is a class that has a bunch of error codes inside. And this is something that I didn't know was a good thing to do. But in general, it helps a lot because you can bundle, you can have specific error cases without having to really guess what the error is or without having to read a printed error message, right? Because sometimes you have errors that you can recover from and you have errors that are not exactly recoverable. So for example, you can use the same status to represent, hey, this item is not found, but your database is still running successfully, it's working, right? Or you can also say that, hey, there's an IO error, right? Or maybe your policy is that you retry on an IO error, right? So instead of simply returning a thinner object, you can probably just, it is advantageous in cases like this to have a slightly more overloaded status code or a return object that gives you much more of an idea about what's going on, right? So you can see, right? You have a method to create a status with the code not found, right? So this is something that I didn't know was common practice, but turns out to be really useful. So it's a good note to keep in mind. Let's go back to the actual interface. Okay, so you can see all methods or most methods here return a status, right? So we've got open here, which gives, so you can see that this is a static method. You don't really need an instance of the database to call open. So you can just do db::open to create an instance of the database. And then from that point onwards, all other methods are methods that happen on an instance of the database. Okay, so this is the interface. You have put, set the database entry for key to value, returns OK on success, and a non-OK status on error, right? Important to keep in mind. It takes write options. So this is some other interesting thing that I found. The level DB interface exposes options for a particular write that you do. So if you want to write one specific pair of keys and a specific key value pair, and there are configurable options here. So right now you can see that this has sync, right? There's a lot of debate, or rather I would say it's somewhat understood in the database community that having, let me rephrase. It's somewhat understood that overly depending on the kernel page cache to write your data to disk reliably is not a very happy path if you care a lot about how precisely your data is persisted, right? So I think this is more of an artifact of evolution, that you can still control whether or not a write is processed through direct IO, where you bypass the kernel page cache. But yeah, one design choice I personally disagree with is making this false. So you are sort of forcing all writes through the kernel page cache. The edge case is if you lose power while your write is in a kernel page cache, the client has understood that, hey, this data has been persisted, but it's really not on the disk. It is still in the page cache. And you lose that write in between if the power dies when you have this write going on with sync false. So I personally think they should have set it to true. Yeah, and this comment substantiates exactly this, right? So anyway, this is one tunable that you have per write. So you can see every put takes a reference to write options. The slice object here is a sort of wrapper around a key value, is a sort of wrapper around a string. You can actually check that out if you want. Yeah, so it has a data and a size, yeah. So char star data and size t size. So you can see that it's a sort of wrapper around char star, and it has a bunch of methods that make it easy for you to use in a more ergonomic sense. Okay. Cool. So you pass the key and the value. You have an option to delete a key. So in an LSM tree, you can, so an LSM tree is an append only sort of data structure. I won't dive too much into LSM tree internals here, but just know that deletes are not done in place. Like you don't go to where the data actually is and you delete it. You write a separate record to delete some data in an LSM tree. Then you have write. So in write, you can take a batch of writes. And one more interesting thing that I learned is that in a lot of more enterprise side or a lot more high performance database systems, batching as a first class primitive is a very common thing, right? So I at least discovered batching as a performance primitive more through exploration and more through understanding that, hey, at times it is more optimal to do it. Having it be a first class primitive consequently makes sense as a design choice. So you can accept a batch of writes that you want to persist at once. Then you have get, which essentially gives you, so again, you have read options here, right? And you can do a bunch of stuff here. You can cache the data that you read in memory, right? You can do a snapshot read. So if you are manually maintaining snapshots of your database and you want reads from a specific snapshot, you can pass that in through the options. And if you're, let's say you're running on storage media that is slightly older or is more likely to be corrupted, you can also have a flag to verify checksums so that you don't unknowingly pass damaged or corrupted data back. Okay, so you have new iterator. This is an iterator over all the contents of the database. Method to get a snapshot, to release a snapshot. So get property, I remember here is, this is another method that they've implemented to do some different, to expose some different methods. I don't know why this has been done this way. I would have passed an enum or something here, but this is mostly going off of documentation. So like, hey, if you want the stats, just pass this string and we'll give it back, which is I don't know why they did this, but so this is one method that's there. Get approximate sizes, I believe this is, yeah, the approximate file system space used by keys in a specific range. Yeah, I don't know why this exists, but it's there. So compact range, so this is a API for compaction. So in an LSM tree, what happens is, because I mentioned that deletes and updates don't happen in place. So in a B+ tree, you go directly, you find the page where the value exists, and then you update that value right then and there in place, right? And as a consequence, you have to deal with things like, what if a page is full, right? So you have to do page splitting. You have a bunch of other performance-related trade-offs that you have to make to have a much more tightly bound log-based 2FN read latency, which is that you have to do a lot of maintenance work to make sure that your invariant and your tree balancing is maintained, right? But in an LSM tree, all your modifications to data happen in a new file. So they're appended to a new file. And consequently, you read in the order of most recently written to least recently written to get the freshest data that you have. So the consequence of this is now that, let's say I have 3 keys, right? So let's say I have A1, B2, C3, right? Let's say I want to modify A, right? So in a B+ tree or in a B tree, you'd go here and you do A2. But in an LSM tree, you have A2. So this is a new record that's appended. So now when you look up the value of A, you go in this order and you see that, hey, the value of A is 2. But now the problem is you have A1 here, right? And this is, for all practical intents and purposes, wasted space. Right? You are taking up space to store an old value at the benefit of having really quick writes. So there's a maintenance process called compaction that runs that essentially takes care of removing all these old values so that eventually your disk space matches the amount of data that you have. And yeah. So this is essentially what compaction is. This is the API to do compaction in LevelDB. So you can either compact a range or you can compact the whole database. Okay. So this is the high-level API that we've got in LevelDB. Any questions so far? No? Okay. Cool. So now, okay, so we saw that this is a virtual, these are all virtual classes, right? So the actual implementation of the database is located here in dbimpl.h. So you can see that it inherits from the interface, and you've got all these methods, you've got all these constructors and so on. This is most of where the money is. So you've got all these implementations of the interface. But I think it would help us to look at some of the slightly more internal structs as well, the internal data structures as well. You've got a struct for manual compaction, which I believe is a tracker struct of sorts to sort of track the different manual compactions that you may trigger. You've got, so sorry. The food's here. Yeah, sorry about that. So we've got this struct here that tracks manual compaction. So you can see that we've got the beginning key and the ending key. The TMP storage, I'm not sure what this is used for. We'll probably learn more when we look at the compaction code path. You have stats here for a compaction. So you've got the time, the bytes read, and the bytes written. What I want to highlight a little more is some of this stuff. So you've got a table cache to cache some tables in memory. You've got file level locks, famously notorious for having different implementations across OSs. And you've got most of the actual LSM tree state here. So you can see that we've got a mem table here, which is the in-memory component of the LSM tree. And you've got an immutable mem table. So how it essentially works is you've got all writes that come into an in-memory component first, and that in-memory component is periodically flushed to disk. And while that in-memory component is being flushed to disk, because I/O in general is much slower relative to memory operations, we want a method to not lose the writes that we're getting. Right? So what we essentially do is we swap the immutable mem table with we swap this mem table, assume all writes have come here. We swap this with the immutable mem table, so that while the I/O operations are happening here, you are still able to flush the main mem table to disk. Okay? So you've got some atomics here. So yeah, we'll get into the semantics of that later. So there's a log. I believe this is the wall. They've implemented their write-ahead log as this. They've used this class called a log to implement their write-ahead log. So they have a queue of writers here, which is something we'll get into. There's a write batch, and yeah, okay. So that's most of what we care about with regard to the writes happening. There is also one of the should be a versions here. Yes. So the version set here, I believe, is the thing that handles how data is stored on disk. So your collection of SS tables. In an LSM tree, you have data stored. So when we flush the mem table to disk, it is represented as an SS table, which also stands for sorted string table. Yeah, we are heading a lot more into LSM architecture. But essentially, the SS table is the file that holds all your data on disk. Right? So there's an in-memory component, there's a disk component, and a lot of how fast your reads are from a performance point of view depends on how you organize your SS tables. So there are multiple strategies. There's a tiering strategy, there's a leveled strategy. It's a very interesting way of looking at the trade-offs that you can make in terms of how often you run your compaction, because compaction, as your data volume grows, can be a fairly expensive process. So we have different tunables with regard to the strategy and performance of compaction. But essentially, all files, all data on disk is stored in what's called an SS table file or a sorted string table file. And you have the version set which manages snapshots or different states of these SS table files. So let's say you write 3 keys and values, and you have a flush that comes in. So when you take the mem table and you write it to disk in an SS table, it's called a flush, right? So you write it to SS table A. Let's say you have 10 more items that come in, you write it to SS table B, right? The version set essentially manages, so if after SS table A is written, right? Let's say you are in the process of writing SS table B, right? Now, part of that SS table exists on disk, but it's not fully written. Right? So how do you know that something has been done? In terms of how do you know that the write has been complete, right? So there is a snapshotting mechanism that tracks completed boundaries of writes, in the sense that if you finish 3-4 writes, you can create a snapshot that later tells you on startup that, hey, this is the last committed snapshot of the database. Making sense? Is everyone, any questions? No? Okay, cool. Okay, so let's get into the test. Okay, so now what I'm going to do is I'm going to run this test. I'm going to debug this test. Okay, it's building. Okay, well, let me see if I can zoom out. Oops. Okay, we need this stuff here. And cool. So on the left side, you can see the stack, the whole stack of what we've got. And we are currently in a single thread, so we don't have to worry too much about that. What I'm going to do is I'm going to step in. Okay. So when we say put, so you can see that there is a DB test class here, which is a sort of test harness, where let's say if you have 10 writes that you want to track, and you want to see whether these writes have made it twist, you need to track additional, in a testing scenario, you need to track additional metadata about like, hey, what's the key, what's the value, right? So the DB test class is a harness of sorts that wraps database methods for convenience. And yeah, so the DB underscore is the internal pointer to the database that they've got. So let's step in some more and see that we are initializing the right options here. Creating the slices. Okay, so DB impl put, it calls into DB put here. Let's step in. Okay, cool. So now we're creating a write batch. So one nice thing to note here is even though you have what is a point API, or like this is not a batch API, right? This particular API, DB put, is not a batch API. But you can see that internally, you are calling the batch API because you're creating a write batch. You're adding this one key value to the write batch, and then you're calling the same code path into, like you're calling the same batch code path. So this is often done sometimes when you don't want to maintain, in general, it's a question of whether or not you want to maintain two separate code paths for point operations and for batch operations. I think most people just tend to reuse most people tend to implement their point operations as a single size batch, so that you can maintain only one code path, and then you can optimize for performance later, to see, depending on, having one code path is easier, I think, in general, unless you really strictly need it. Creating a batch, you're adding the key value to the batch, then you're heading into the write method here. Let's step in. Cool. Okay. So now that we're in the write code, before we step over, I actually want to point out something interesting. So you see, we saw this writers here, right? And we can see that it's a double-ended queue of this writer object here. You can see that we are sort of waiting on a conditional variable here. So the contract that LevelDB offers is that there is no external synchronization. There's no need for external synchronization, right? So as someone who's using LevelDB, you don't have to slap a mutex on top of LevelDB and say, hey, I'm going to synchronize the access to the actual instance of LevelDB. A lot of the synchronization is internal. And that's sort of the contract that they offer, that you don't have to worry about synchronizing between different threads in your application when you want to write. Okay, so we've created this writer. Let's just step into this. So it says the information kept for every waiting writer. You see that it takes a mutex that it keeps. It initializes I think this calls a constructor of the condition variable with the mutex. And we've got a status here, we've got a batch of writes, we've got two booleans, synchronized and done, and we've got a condition variable that we're seeing. So I'm going to step back. I'm going to step over. So now we have an object that carries this mutex. Let's inspect what's going on in this object here. The writer. You have the same stuff. You have the status, you have the batch, you have a condition variable. The condition variable seems to have taken the mutex here, a reference to the main mutex that we have. So we passed and mutex underscore. So there's mutex underscore. Do we have an address? No, we don't have an address for this. But yeah, we've passed the reference to the top level mutex in level DB. We have the mutex lock is an RAII or we can say scoped lock here. So when this object dies, we automatically release the lock. So that is what we've got here. And we see that we are doing a pushback, or rather we're just pushing into the writer queue, right? So this is one thing that sort of stood out to me quite a bit when I was going through this code base initially. Why is there a writer queue here, right? Because if you look at it in most other languages, right? Like you've got synchronization that doesn't happen, or rather this particular way of doing synchronization is new to me, in that you have the queue inside here and you are waiting within the main writer thread itself, right? Because when the user calls this code, this db impl write is going to execute on the user's main thread, right? So it seems a little odd to me that the user is waiting here. So once we've pushed back to the writer, it seems a little odd to me that we are waiting here for the queue to drain. Because in most other languages, I think you would sort of lock an internal resource again, and you would sort of wait for the kernel or for the language scheduler to let you have access to the rest of the code. But maybe they've seen something that I haven't seen, and this is probably the more optimal way to do it. So currently, there's only one writer in the queue. So we can validate that by looking at, should see writer underscore here, writers. Yeah, so this is a DQ, double-ended queue, and we have only one writer, which is us. Okay, so the condition is while the write is not done, and this current writer is not at the front of the writer's queue, we wait. So this is a conditional variable, and we wait. We are at the front of writers because there is only one item in the queue. And we want to see if the write is done. This bit is a little confusing as well. Like if you are waiting for the current write to be done, why is there a check to see if it's been done in some other thread? So this is something that stood out to me as a little interesting. So while you're done waiting, there's this thing called make room for write. What essentially can happen is, so when you look at an LSM tree, right, and we organize the data into different levels, there's one contract that you usually maintain for performance, which is that the key ranges in level 0. So let's say there are 5 levels in the LSM tree, right? So there's level 0, 1, 2, 3, 4. In level 0, all the data that comes into memory is directly flushed without worrying too much about ordering. And in every other level, you are guaranteed that one key belongs exclusively to one file in the level, right? Now, this invariant helps a lot from a performance point of view, because you're ensuring that if I want to look up for one key in one level, at max I have to only open one file. And because every time you open a file, you have to do the whole syscall chain of opening the file. And the read is sort of an expected cost regardless of where you are, right? Because that data is on disk. But you still have to go through the syscall cost of opening the file, of getting a file descriptor, of everything that you need to do before you read, right? So having that invariant where you have one key is located only in one file is a very helpful one from a performance point of view. Now the problem is, when you write from memory to level 0, which is where all data ends up first, right? You don't really care about maintaining this invariant because that would slow down your writes by a large margin. The whole advantage of an LSM tree over a B plus tree is that your writes are really fast because you don't have to do page splitting, you don't have to go find the key, you don't have to do all of that. You just dump it on disk, which is why it's much faster, right? Now, if you had to sort through all the levels, if you had to search and then figure out where to put the data, that is a performance hit that you ideally don't want to take, right? So in level 0, you usually just tend to dump data as is. And the consequence of that is that you have overlapping key ranges. Let's see if there's a diagram that. Okay. Let me see if there's a good diagram for this. Something that hopefully has the key ranges here. No, that's a B plus tree. It's a B tree. Okay. Content, not mine. Disclaimer. Okay. So, in essence, this is what happens. So this is your in-memory component. It gets flushed to disk in level 0. And there is no sorting being maintained in level 0. There's no ordering invariant being maintained. So within the SS table itself, it's sorted. But the key ranges can be overlapping. But here, in these other index, so let's say this is D to F, and this is H to K. Right? So you are sort of guaranteed that none of these key ranges overlap. But because that's what you need to ensure that you have only one file, right, that you have to look up. But here, you can't really control that. So in essence, what you end up having to do is you end up having to scan a large number of tables in L0 to serve your read, which is why even though net you have smaller SS tables in L0, the read latency is dominated by the number of files you have in level 0. So it tends to be directly proportional in that if you have more files in level 0, there's a higher chance that you can have more than one file that you have to check because the key ranges are not guaranteed to be non-overlapping. The key ranges can overlap, so you might have to read multiple files. Now, to manage this, this make room for writes function has this thing called level 0 slowdown writes. So it's a tunable that if you say that, hey, I have 4 files in level 0, and that is the max number of files I want to read in level 0, right? So what happens is you check, so this basically just checks to see if there are too many files in level 0. And if there are, it means that the compaction process, which is also responsible for maintaining not just space usage, but also tree shape, right? Because we want to ensure that we don't have too many files. There are different criteria based on your compaction strategy that control your latency in terms of your read latency and in terms of a bunch of other operations as well that you might have, maybe larger compactions and stuff, right? Or your point lookups, basically. So you want compaction to maintain the invariants that you've got, which is that, hey, one level can have, so if your policy is that I have 5 MB of data in my first level, I have 50 MB of data in my second level, 500 MB of data in my third level. If you have a multiplicative factor of 10 of sizes across the levels, that controls your compaction, basically. So if you have too many files in level 0 beyond a threshold, it essentially means that your compaction is lagging for whatever reason, right? Let's say your disk slowed down, whatever happened, right? So this function essentially does a sleep in the right path to ensure that the compaction has a chance to catch up, right? Because again, if you can trade off, like if you can do this compaction now to ensure that all your reads are faster, sometimes it's an okay trade-off to make. This is predicated under the assumption that this does not happen very often. Because if it does happen very often, then you are hurting your performance on purpose, right? And it's also a question of whether or not you want to optimize for a specific type of latency. This is in the tuning territory where you look at the specific use case that you have and you decide, hey, what am I okay suffering with at what benefit, right? So interesting function to look at. And okay, so now we see that we have this thing called the last sequence. So this is the sequence number. The sequence number is a sort of monotonically increasing number that every write gets assigned. And you use this to sort of see, hey, if I'm reading some data, so let's say my snapshot has a high sequence number of 100, and if I've written till 102, then I know that my snapshot is behind without having to exhaustively check through all the data to see if who is out of touch and how, right? This also helps a lot in recovery, which we're not going to go into right now. But essentially, you get to store the sequence number. You have the last writer. This, I'm not sure why this reference is being captured. Updates is not null pointer. So we build a write batch here. This is interesting. I don't know why this exists. What does this do? This looks like some validation and probably some splitting to ensure that your batches are not too large. I won't dive too deep into this. It seems like there's a lot of nuance here. We're setting the high sequence number +1 in the batch. I think this is a temporary write batch, if I'm not wrong. Not sure, but we can go ahead. You're tracking the last sequence number as the known last sequence number plus the number of writes that you have. So if your sequence number is 5 and you have 5 writes, your high sequence number after that is going to be 10. Right? So if we take a look at our last sequence number now, so it's 0, and it's going to be 1 because we're writing 1 after this. Right? So let's assign a watch on this. Let's go here. So my bet is that this goes to 1, and it did because we have one item that we're writing. Okay. Now this part is interesting because it says, so this is the core of the write where you write to the wall and apply your mutation onto the mem table. It says we can release the lock during this phase since the writer object inside the queue is responsible for logging, which is the wall write, and protects against concurrent loggers and concurrent writes into mem. Not sure how that happens, but worth looking into. So we unlock the main writer mutex here, and we call log add record. So this is the wall. The write ahead log is a crucial piece for recovery and different levels of fault tolerance. So we've got this here. We've got so what we're doing here is we are writing data to the wall file. Yeah. So you see this emit physical record. So this is what actually writes the actual record into the wall. I'm just skipping ahead so that we can jump over this function and don't have to follow the call chain fully internally. We're computing the header for the record. We have the CRC and we have this. So this is where you actually write the header and the payload here. So you're checking status to see if it's okay. Once you append the header, and then you can append the actual data. And if that's good, then you flush. So the writer here is also buffered, maintains a buffer internally that you can then flush to disk. And then you can, so this, over here you're manually calling flush. So I'll head back. Yeah, so that's the wall write, basically. Have a way to see if you have a sync error, which we don't, so we're good. So we skipped over that. This is the interesting part. So this is where you're inserting your data into the mem table. So let's step in. You have a mem table inserter. You have the sequence number tracking. And so B here, I think, is the batch. And you have a iterate method that calls a callback on every item in the batch, which I think is exactly what's going on. So we're iterating. Type value. So we're calling handler put over there, or maybe we're just checking the conditional here. Yeah, missed that. But the handler put method here essentially does the actual insert into the mem table. We've skipped over it, so we can't really dive into that. But anyway, so we're at status okay. And so this is in the write batch. And at this point, we've successfully inserted data into the mem table. Now we are good to acknowledge the write to the user, right? So you can see that the first thing we had to do is ensure that data is actually persisted to disk in the write-ahead log, and then we wrote it to the memory, right? It is not okay to return without doing either of these things, right? Technically, you can return after writing just to the wall, but if you then read something that you've inserted, your performance is going to be really bad because the expectation is it's in memory, but it's not, it's on disk. And you'll have to optimize your read path separately to read from the wall first, which is fairly messy and not something you generally want to do unless you're doing recovery. So then we're locking. If there's an error, we're sort of checking that we can record the error. It looks like there isn't, so we don't go into this branch to record the background error. There's a temporary batch here, which I don't know why it exists, but it's probably worth looking into. And the important part here is you're setting the high sequence number now internally, right? So you're updating the high sequence number and saying, hey, we've written until this number. And in general, both your mem table and your wall sort of track the high sequence number. So because the wall needs the high sequence number for recovery, so it can know from what point it has to replay data, right? And that is a brief summary of the write path. So I hope this has been somewhat useful. I hope this has been somewhat useful in terms of seeing, hey, this is a fairly new unknown code base. This is how we try and make sense of what's going on here. I'm not an expert in this, but this is what I've been able to sort of grasp. And I hope this is a good place for more folks to start looking. Hopefully this encourages you to take a look at a strange unknown code base and try and make sense of what's going on. And the debugger thing is something I learned from one of my managers at work. So debugging unit tests is often very helpful. Instead of guesstimating and trying to figure out what code paths actually take place, you can just see it, right? And unit tests, if you have unit tests, it's a great advantage because you can then figure out exactly what code is being executed. So that gives you a pretty useful handle of the whole flow of the code. And I think that that's a nice way of learning that deserves to be talked about more, which is why I'm doing this. So yeah, thank you so much for your time. I hope this has been useful as a sort of walkthrough of how LevelDP does its writes. And yeah, that's it from me. So thank you. Any questions? Yes. 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 Does it create? It depends on how you define write amplification specifically. So the definition for write amplification that I know is that once you write a byte to the disk or to the storage engine, and it varies, like different engines choose to define it slightly differently. But essentially, once you write a bit of data to disk, how many times is it rewritten, right? I think in this case, whether or not you use the page cache, you're still doing a write. It's just that the performance impact isn't felt as much. But from a definition point of view, and I'm probably arguing semantics here, but from a definition point of view, it still counts as a write. So it probably is not impacting write amplification that much. So yeah. It's very transparent to the user, right? So the user doesn't really know whether well, technically they do because you can control it via the flags that you pass into the write syscall. But yeah, I don't think the impact is. This is one of those things where like you're okay losing the data in the event of a power, and it's a rare thing, right? Like it's not every time that you expect like power loss to happen and your data to be lost, but you do have to sort of build for these things. So unless you're like doing a cache or something like that where you're okay with losing data a little bit, then you can trade that performance that you get by not using direct IO for having lower latency. So yeah. I hope that answers your question. Sorry, it's not a very clear answer. Awesome. Yes.
I'm not sure this is something I should be asking, but is there anything like architecture-wise that Rocksdb does?
A whole bunch of things. So RocksDB started as a fork of LevelDB, but the design choices have significantly evolved since then. So the concept of column families, which I believe is a way of sharding, I'm not too familiar, but RocksDB has done a lot of performance improvements, and in general, it's good to go through their features and their release notes to see what they've been building. So one thing off the top of my head is they introduced an auto tuner for compaction rate limiting. So compaction is an expensive operation, and they introduced so they have a rate limiter for compaction where you can say, hey, I want X bytes per second happening in my compaction guaranteed, right? Because if you have a large amount of data and you do a compaction, right, you're using a lot of I/O, and especially in a deployment sort of scenario, it is concerning because there are other applications that need to do I/O on that same node, and if your compaction is drinking up all that I/O, then the other things that need to do the I/O work can't exactly access the disk as efficiently as they need to. And in general, you might want to control the utilization to maintain lifespan of your disks. So they have a rate limiter for compaction, and they recently, I don't know if it's recently, but yeah. So they have something like this. It's an auto-tuned rate limiter for compaction. So they do a lot of very interesting work in essence, and it's generally worth looking at how they do, and it's probably a good code base to start reading as well. It's fairly clean. It's like pretty clean C++, so that might help. And yeah, cool. Any other questions? Yes.
Earlier you said like batching was optimal. So is that purely from an I/O perspective, like switches are reduced or something else is involved?
It's a good question. I think this is more from a perspective that if you were to implement everything as a single point operation, there are some things like locality that you can't really take advantage of. It is very implementation specific. Maybe it's something like, hey, my driver is optimized for batch writes. So you implementing batching in your database is a way of taking advantage of that batching for performance. The same goes for lookups as well, right? So for example, if you have, let's say you have a cache that you're reading from, right? It makes sense for you to batch your data according to your cache locality, such that you take advantage of data being in the cache as much as possible, so that you don't have to deal with having a cache miss more often. Am I making sense? Okay. So that's kind of why we do batching. It's sometimes to take advantage of hardware. In other times, it's dependent on your implementation to see that, hey, maybe I can do better by having less context switches, or maybe less context switches, or like, yeah, there are a whole bunch of reasons that you might do batching. These two are the ones that are coming to the top of my head right now. Any other questions? No? Cool, I think we're good. Thank you folks so much for listening. I hope you had something useful to take away from this, from me rambling. So yeah, awesome. I think we have snacks. Yeah, or do you want to do your talk? Okay, let's break for snacks, or do you folks want to do the second talk right now? Okay, show of hands, who wants to have snacks now? Okay, looks like you're up.
Is this working? Yeah. Cool. Yeah, I know. Still coming through. I think it's still going to be there, but okay, it's fine. I have hotspot. Hey everyone, I'd like to start talking now. Hey everyone, hi, hello. So, hey everyone, today I'm going to talk a little bit about the full text search and a vector search index that I work on. Yeah, so this is the a repository. It's like fully open source. I don't know if you can see clearly, but you have we have around 11K stars, which is super cool. Yeah, so I want to talk a little bit about what full text search is, how you can implement it, and maybe a little bit about how we implement like KNN or vector search and vector indexing, which is currently the hot topic right now. So I don't have anything prepared, so you'll have to look at my Excalibur. So typically you have words, you have a document, maybe you have an Amazon product, which looks something like product name. Okay, cool. Is this better? This is good? Okay. Yeah, product name, I don't know, Havells water heater, for example. You have a bunch of text probably talking about what it is, information about the, I don't know, the capacity, wattage, etc. So you have a bunch of products essentially like this. This is one such product. You probably have let's say 1 million such products. You want to put this up on your website, and you want you want your customers to be able to search for certain certain products. So the naive way of implementing something like this is you basically maybe map each of this text to a doc ID. So this is a doc ID, like maybe, I don't know, doc 1. Or let's say a product 1 for a simplicity. Each product would have this line talking about what it is, and we would probably do a brute force search over the query text which the user has entered, over all the product text. But this is inefficient. You have to iterate over all the words, over all the products for every product, and this is not great. So the main structure, I guess, of an FTS index, or what an FTS index introduces, is this idea of a inverted index. So instead of searching through a product first approach, in this sense, like you're iterating through the product, searching for text, you instead iterate over the text itself, and then you map those back to like a product IDs. So what an FTS index would look like is you'd have terms. Basically, you'll have term 1. If you have information about, like, say this has a keyword, like, say this mentions the word like water somewhere. What your FTS index would do internally is it would store individual words and map them to like a product IDs in this case. So it would know for sure that water is mapped. Let's use a better. Product 1, water might be mentioned in product 4 as well, and then so on. Now you might also, you obviously have a vocabulary of words, so not just water, you have probably grass, green, whatever, and you have so on and so forth. So you're basically mapping every word in your vocabulary to some keys, which will be your product IDs. So what you can do is, if you have a query, like if your query string is green water heater, you would iterate, you would find where these, you'd basically split this up into simpler words or tokens, like as we call it. So green, water, heater, each of these are independent tokens. We would then find these tokens in the inverted index, which key these product IDs. So we would find green, we would iterate over the list of products associated with it. We take water, iterate over it, and then we would take an AND, like we do an AND operation. So all the products that are present in both water and green, we would we would return the list of products that occur in both of them. So this is essentially how an FTS index works. There are some details about how you would want to order, how you iterate over. Here's my cursor. How you would iterate over these keys in the first place. So have you all heard of a trie as a data structure? So essentially, we use something that's kind of like a trie. You will have let's say W, A, T, E, R. And we'd use this to iterate over water. But because you probably have a data structure with a lot of different keys in it, to sort of compress the keys and to make the iteration more efficient, we would combine the prefixes. So instead of what's another word I can use? Let's say maybe ING. Let's just assume this is a single letter, for example. So for R, we would, if the word, for example, terminates at water, we would point this to a list of a product. So like this index is on disk, we would store the associated with the end of water, we would store a address which points to the start of this list. So it would iterate from product 1, product 4, and so on. And if it's a watering instead, we would get information from the end saying that where the watering thing would start, the list of products that have watering in it. Yeah. So the main thing which happens here is it's kind of like an LSM architecture. Not really an LSM, but kind of like an LSM. We don't have the concept of like. So as I think Rauji presented a picture of LSMs having distinct levels, level 0, level 1, so on. We just have the concept of immutable LSMs. Let's just call them LSMs. We create them in memory, and then they are put in a queue, and we have another process that keeps merging them and putting them to disk. And this merger process also keeps checking if the number of these LSMs if there are a large number of these LSM files that we are storing, it would periodically merge the smallest of these files and create a new larger LSM and store that on disk instead. So the main thing, this is essentially the FTS part, which is fine. Now let's come to the vector indexing part, which is far more interesting in my opinion. So vector search algorithms, I think there are a couple of famous ones like IVF, HNSW. You all would have heard of this at some point of time. If you're into vector search and stuff. FTS, or our indexing library specifically, uses something called IVF, which is actually super similar to how an FTS index works. We essentially what we do is if we have a bunch of if we have, for example, if we have a bunch of vectors, like we have n vectors, we would create we'd create centroids through these. So we'd probably create k centroids. So k centroids. So C1 all the way to CK. So and then how you would perform a search is, so these centroids are sort of you create you group a bunch of these vectors under a centroid. So what you can do instead of doing an exhaustive search, if you have a vector, you want to find the closest k, or if you use k, the closest 3 vectors. Instead of doing an exhaustive search over all n vectors, you can do an exhaustive search over these k centroids. K is guaranteed to be typically k is taken to be much smaller than n typically. So this will be an inexpensive process. You find the centroids that are nearest to your query vector, then you can now you can look at those centroids, and then you can look at the vectors associated with those centroids, and then do an exhaustive search over them. So if you have 10k vectors, for example, you have 5 centroids. That's 2k vectors per centroid. If you take only the top 2 centroids, I don't think this is a good example, but if you take 2 centroids, that's 2k. That's only 2k vectors you'll have to compare against instead of the full data set essentially. So yeah, so this is how an IVF algorithm works. One neat thing which we do is the main use case of having both FTS and a vector search as one index is something called hybrid search. So the main thing with hybrid search is you can do an exact match query like green water heater. Like full text search will make sure that the results that it returns will have these words. I mean, depending on how you configure your query, green water heater, the product should have green water heater as part of its as a characteristics of the product itself. Whereas vector search is more loose in the sense it tries to find sentences or queries or queries that are or products which are like semantically similar to what you want, but not an exact match. So it might, so instead of water heater, it might match with an I don't know, a stove, because it is a heating appliance. It's what you use at home. So it could match with stove instead. So people use like hybrid search, essentially a way of doing a full text query, doing a vector search query, sort of combining these results in some way, and then returning it to the like user to sort of hopefully get a better set of results than with just pure FTS or pure KNN search. So the way we do it, so typical vector search indexes, they have a I guess a monolithic index is the way to say it. Like if you have a bunch of vectors that you want to index, all of them will be part of the same index. This has its pros and cons. The pros are that you just have one index to maintain, which is nice. The con is this index can grow to be very huge. In which case you might have to split it or shard it into multiple smaller indexes. And vector indexes are notoriously not great with updates. So if you try to update an existing a vector index with time, especially as if you have a bunch of products on Amazon, maybe in 2026 the products that are certain types of products will be is bought more frequently, whereas in 2027 the type of products that are on the store and that might be purchased won't be the same. If you don't train, so this process of creating centroids from this from a set of vectors, this is called training your index. If you try to insert 2027's products into 2026's like vector index and the centroids train on 2026's index, it's probably not going to be great, because the centroids are not representative of the data anymore. So just doing an exhaustive search of the centroids going to the vectors associated with them is probably not going to give you the accurate set of results that you want. So for a large monolithic index, especially with time, data drift can happen, and that is an issue. With full text search, with our full text search library, we take a different approach. Instead of having a single monolithic index, we have multiple smaller indexes, and each of these vector indexes are completely independent and are located within each LSM independently. So if you have each LSM has a set of products that it indexes, that will have the full text index and the vector index for those products will always be on the same LSM, I guess. So the main advantage of this is we don't have this problem of drift at all, because what we will do is when we want to merge these segments, if you want to merge 3 of these segments, we take all the vectors, we would train a new vector index over all these centroids, and then create a new vector index and then put that on disk. So this means that your vector indexes are going to keep changing and adapting to the new data that is going to be ingested by the index. So that's a pro. So the con of that is we have to do a scatter-gather sort of search where instead of having to query just one index, we'd have to query all of these like vector indexes, which is not guaranteed to be as efficient. But yeah, it's a trade-off. The other niceties that we get through in having a, you know, like a vector index per a segment is we can like filter by fields that are present, that by other fields that are like non-vector fields that are present in the doc. So if you want to filter by green, for example, you can do a pre-filtered query where you say, you know, find me the closest k vectors, but they must have green as part of their name, for example. You can do that in an FTS and in this architecture, because you can easily like filter by query, filter by terms, and then because, as I mentioned, the vectors and the full text index is sort of located in the same structure. Yeah, that's all I can speak about off the top of my head. Yeah, that's about it. Any questions? Sure. So, I mean, typically, like, so I talk about okay. So currently in production workloads, you'll see like hundreds of millions to billion scale like vector indexes. That's the trend now. In fact, there's a trend right now to use like object storage to store like trillion scale vectors as well. But this isn't object storage, so I'd say 100 million or so would be our would be how much we can store. Right now we are capped around 4,000 DIMMs, which I think right now the state of the art embedding modules are around 2K DIMMs. So for now we are safe, but probably in the future you might have to increase that. Right. Oh, yeah. I forget the name. Yeah, I know what you're talking about. It's the yeah. So okay. So like one thing which we can like it is there, but I think some other vector indexes do this. I think Lucene vector search. I think Lucene. Okay, I don't remember what. I think it's called a BKD tree. I think they have a implementation, but apparently it's not very scalable. So it's not scalable in the sense of like the number of DIMMs that we'll have. It's good for like geo queries, for example, where it's like DIMMs are in a lower number. Whereas if you go to 128, 256, like 1,000 DIMMs, normal like our IVF and HNSW algorithms end up being smarter to use. Sorry? I'm not familiar with the BSP tree. BKD trees. BKD trees. So per DIM, you're sort of like partitioning your space. So if you have just like if you can think of a single number as a one DIM vector, right? If you have a bunch of numbers, you can say like if it's greater than 5, the values will be on this side. If the value is less than 5, the value will be here. Now, if you have a 2D vector, you'll have it's like a quadrant, so it's like 4 spaces. So you can go to a quadrant and then do a search, and then that keeps 2 power n for the number of DIMMs that you have. and then you keep like doing an exhaustive search on the quadrant or octant, I think, or whatever. Yeah, for 3D. Yeah, yeah. Any other questions? Yeah.
This was regarding the vector index that will be retraining or remaking, right, each time of the query. And you had pointed out a trade-off that you also have to query all the other indexes that may not be efficient.
Yeah.
One way that you said you can mitigate it is by querying for those where the filters are present in the document, right? Document metadata.
That's not a mitigation, that's an access pattern, like in the sense of if you have a like use case where you need to filter certain vectors only by, you know, like green, for example, as part of that name, then it makes sense to use a full text search index. It's not a way to solve this problem, I guess.
Shiva, would there be any way to for somebody to tune the way that they're looking through the indexes? Because the indexes may grow. These indexes that you keep making, is this a number that will keep growing as your data gets bigger, or you keep so it will grow?
It will grow. So like these LSMs initially will have you'll have a large number of smaller LSMs, but as the data becomes larger and larger, these LSMs get merged, and so you will have larger segments or larger LSMs, which will have larger vector indexes as part of them. So yeah, they will be bigger.
So they will get bigger. And is there a way for someone to tune what they would want to search through? Is there a metric, or maybe because I don't know much about this, so how would somebody make that optimal, which index to go for? Because if you are going to a non-efficient index, then you are definitely going to spend a lot of compute searching through.
Yeah, but but that's the issue with vector indexes. No, you can't just you. The reason why we have to do this exhaustive search, like for example, is to find like you can't just do something like query like green, just go to the like list associated with green and then iterate over that. You do have to find the closest centroids first, and you don't know where the closest centroids are. They can be across multiple indexes. Now, if you did have a pre-filter saying green, you could probably filter segments if they don't mention green at all anywhere. Then you can just be like, cool, I can ignore this, the like vector index on this segment, which is something that we do. But if you're looking at pure like vector search only, we have to do a scatter gather across all segments. There's no other option. Yeah, no issues. Anything else? Yeah. Okay. I'm not too familiar with FPGAs, but that would be cool. Um, I think there is a lot of tech going on right now to like run search workloads on like unique hardware, like GPUs, for example. Like a vector search on GPUs is currently the big thing. So maybe, hopefully, that would be nice. Yeah. But yeah, I don't think like that's an industry-wide thing right now. Cool. Anything else? Cool. Thanks so much for listening to my talk. It was fun. Um, I'm sorry it was kind of in the moment. I sort of figured I'll talk about it, but yeah. Thank you.
Very quickly before we break for snacks, a massive thank you to the amazing folks at Pre6 for giving us this awesome space to have this. Thank you so much for
This one's okay. So this is back online. Just pull that down to make sure it doesn't buzz. Folks, our last talk is an unplanned talk, but it's about how we are streaming our video today. So for those of you who have been curious about how we did it, this is what it looked like 1 year ago when I started working on this project. And so this is for those who are interested in what this setup is and how it's supposed to work. So there are multiple things here. It is not going. So it's not possible to cover this in a single talk. There's probably 1 week's worth of material if you go into each of these subsystems and how much pain they can get to be. So I guess we will start off with talking about the non-obvious parts of the problem, which is, so if I have to give you a quick summary of how this thing works, it's essentially just a PC with a bunch of capture cards. And all I'm doing is capturing one video source from a laptop, one video source from a camera. Today I'm using a webcam, but we could have done it any other way. And it's really trivial. Okay? All of you have the equipment to do this. If you don't have a capture card, it's like 1,000 rupees, go buy one. And today evening you can be doing streaming the way we are doing today. It's ridiculously simple. That is not the problem. Okay? The problem is always in the cables. Okay? The stupidest possible source of problem, all of these cables, all of them have quirks. They misbehave in ways that you do not expect them to misbehave, and they misbehave at the most inopportune moments. And so if you're trying to solve this in a way that says that I can just walk in somewhere and start doing a broadcast, the actual solution is, can I do this without any cables? And so if you look at this, most people have a phone which is a fairly good camera and fairly good at streaming and fairly good audio, and you can do a broadcast from your phone, and it works perfectly well. The only problem you got is that you can't capture a slideshow on your phone because that's a laptop, and that is typically where it comes to saying a phone is not good enough, even though by itself a phone is fantastic camera, fantastic processing power, fantastic ability to live stream. All of that is already solved. You can even, there are people who are doing full-scale cinematography using mobile phones, and they're good enough for that. Except when you want to capture somebody's slideshow. And then you have an external source, which means a capture card and a cable, and then your life becomes hell. Because the cable that gives you all of your headaches. And so this tends to be extremely unintuitive. So, but it's what you learn from experience. And so when I started this project, my first idea obviously was to say, why don't I just use a cell phone and just figure out the capture card problem, and then we are in business. And then it turns out that that way is a lot of pain, so maybe you should do it with ARM and just use a regular ARM board like what I have down here, a Raspberry Pi. And I don't know if you can make out clearly over here, but there's an orange cable and there's a white cable. That's because the Raspberry Pi 5 has two camera serial interfaces on the hardware, and that means you can connect two cameras to them, to that board. And here what I've been trying to do is, one, add a capture card that's sitting under the Raspberry Pi, it's a hat. Another one is a Raspberry Pi camera. And so it started off with the simple thing of saying, okay, if I can't do this with the phone because they're lockdown ecosystems, let's take the equivalent of it, which is an ARM board, which has a camera interface, which is exactly the same thing as what's inside your cell phone, and try to assemble hardware from here. And this got me down into Linux kernel driver hell, which I could give you a 10-hour talk about. So I'm just telling you that it exists, and maybe we'll do this in a future meetup where we go into each of the subsystems and what kind of pain we can expect out of it. So my initial attempt at saying that I'm going to go in and do it with ARM didn't really work out, but learning why it didn't work out took me several months. And in the process of doing this also, the other thing I realized is that if your life is difficult because cables misbehave, then maybe the way to solve it is lock away the cables inside a box so you don't touch them. So can you take something like a PC cabinet, but customize it to say put all of your additional audio and video gear inside the cabinet, close it off, and don't touch the cables. If they're working, leave it as it is and take that unit. And that's basically what this is. It's a PC cabinet. But to get to making a PC cabinet in this very weird form factor, I ended up being on a circuitous journey. And one of my explorations was with this fancy thing you see here. It's a server rack. It's a miniature server rack. Now, server racks are typically 19 inches, and they tend to be about 6 feet tall, and that's what goes into a data center. And that's an extremely old standard. There is a more recent standard that's called a 10-inch server rack, which is half the size of a 19-inch server rack, and this is it. And so I figured, okay, look, why don't I buy one of these miniature server racks? And because they're modular, unlike a desktop PC cabinet, which is meant for motherboard plus things that go on a motherboard, and not really for adding on whatever you feel like, PC cabinets are not great for that. So why don't I, build a sort of a server rack? So I bought this stupidly expensive server rack, and then I realized I didn't like it at all. I mean, it's very nice as a server rack, but not as a portable rig. And eventually, I ended up looking through the specs of how a server rack is built, and I made my own using aluminum extrusions, which is the little thing over there. And then what size should this thing be? This is the 4U spec server rack. 4U turned out to be not the correct size. So I went through a whole round of trying to figure out how to do this. And all of this stuff is on GitHub. You can look up this mini rack GitHub project. It's got all the CAD files in it, the ones that I iterated through. There's a long blog post here that explains in more words than anybody should be reading how I discovered how to make server racks with aluminum extrusions. And if anybody wants to guess what this fancy thing cost, that's not enough money. That thing as a box is 16,000 rupees. Okay? And the only reason it's so expensive is it ships as a box full of empty volume from China. And shipping is by volume, not by weight. Okay? And so because they send it as a fully assembled empty box, you pay 16,000 rupees mostly to do with shipping costs and not the actual value of the damn thing. So I built this one, and because I was trying to say I want the same thing but half the size, I wasn't very good at sourcing components effectively, so I spent about 4,000 rupees on this box. Okay? And since then, I've learned how to buy correctly, and now it costs me less than 2,000 rupees per box. Okay? And that's just about learning how to navigate SP Road and find good deals. So one half of my journey was just saying that, okay, look, I want to take a server rack spec and make a box. What size should that box be? You can see I went through multiple sizes, trying to figure out what is appropriate for what I'm trying to carry. And then this question comes up of how do you mount stuff to it, which forced me towards saying, let's standardize on the box in a somewhat stupid fashion, which is make it a cube. So that once it's a cube, it's the same size in every orientation. I can do jigsaw Tetris with this, stuff equipment in from any side, and I don't have to redo the mounting frames. And so a lot of these frames were, they're all 3D printed. I had to learn how to CAD to figure out how to make these things. It turns out it is easier than we think, and CAD is programming, it is not art, which is not intuitive when you enter this thing, but it's basically, you write it out as programs more than anything else. I'll take you through a bit of it when I went through this. So the first part of it was entirely about saying, how do I make a box that is designed to carry anything, and you can bolt on anything to it? And aluminum extrusions, as it turns out, are what's used to make windows. And therefore, pretty much anywhere in the world where people are making buildings, you can buy these things for dirt cheap. Yeah, in fact, the cheapest source I found for this particular form factor is called 2020. That's because it is 20 this way by 20 this way, and whatever length you want. The lowest cost I found is about 270 rupees per meter. This particular box has about 2.7 meters worth of aluminum in it. So that's roughly what, about 1,500 or so. Yeah. And so I went from 16,000 to getting it down to that much, just by learning where to buy it and how to cut it. And then because I made it a cube, it made my life easier in CAD, because then I could fit equipment in from any side whatsoever, make sure all the cables are connected and then close it off. And then now I can bring it to some place, and the only remaining cables left are the presenter's laptop, the venue's sound system, and the camera if it's outside the box. So right now I have a camera inside the box because that was one of my optimizations saying, look, that itself adds 10 to 15 minutes of debugging every time something doesn't work. So can I not have an outside camera? Can I just put it inside the box itself, and all you do is pull it out now? And pulling it out obviously means you move the cable, which means something will go wrong and it will not work, as we had this morning when we were debugging. But underappreciated fact, it's your cables that are 50% of your pain, not any advanced technology. And so as long as you remove access to cables and unplugging and replugging cables, you will solve most of your problems in building a setup of this kind. So as for why cables cause a problem, every kind of technical subsystem has a different version of why it becomes a problem. And let me give you a simple teaser of what kind of problem to expect. It's not in any of these photos, sorry. But when you plug in something into USB, okay, let's say I have two capture cards on a computer. They are the same model of capture card. I put them on two different USB ports. And I'm trying to do a layout for my stream in which I have the presenter's face showing up on one side and the slideshow showing up on the other side. So let's actually look at the video for this slideshow. So if you go to Bengaluru Systems 17, it's currently playing live. I will mute it so that we don't listen to myself. But here we are. Okay? And that camera is not pointing at me. So let's turn it and point at me. There's probably about a minute's delay there, after which it will catch up. Okay, and so if I unmute myself, you'll hear me through this computer. That camera is not pointing at me. So let's turn it and point at me. There's probably about a minute's delay there, after which it will catch up. Okay, so I'm here. So now we just want a split screen layout. I have two capture cards. And so if I unmute myself, you'll hear me through this computer. Yeeks. Okay, that's muted. So you got two capture cards. They're the same model. You plug them into a computer. You've defined your layout, and the software I'm using is called OBS. It's open source. You can download it and start streaming today itself. In OBS, I said, look, I want one camera's feed to be on this side of the screen, the other camera's feed to be on that side of the screen. Okay? Now, how does OBS know which USB device is which camera? Anybody wants to take a guess? Okay, so what is the identifier for the device? Is it the vendor ID and product ID, which is the USB identifier? They're the same model, so they both get the same IDs. Okay? Or is it the USB tree location, where you say that I'm referring to this particular port, and the camera on that port is what I've mapped to my layout? Or does the device report a serial number? Okay? And then you say that based on that particular serial number, I know that even if I put in a different port, I know which camera it is. Okay? So who wants to guess which method is being used? The thing is, we don't know. Okay? And we don't know which version of the software does which method. Okay? It is not consistent. So this is your first thing you're going to deal with. That every time you unplug and replug a device, the mechanism by which it is identified to your software, you do not know, because while you thought that it is doing this method, they put out a software update in which they changed the method, and you didn't read the release notes. Okay? And so this becomes one of your quality of life problems with cables. Okay? That a simple thing like I just unplug the cable and put it back in fact, what we have discovered as of this morning is that whatever is happening in the current version of Windows and OBS, the same port, same device can have two different identifiers. Okay? So we have had an issue today with the capture cards crashing for some reason, and the only way to reset them is to unplug and plug it back in. And when you do that, it gets a new device ID. And then you tell OBS and say, stop using that camera, use this camera. They both have the same name. And in fact, they are the same device on the same port, but OBS thinks they're different devices. So this sort of thing is most of the problem that we're trying to solve. And that's why you put everything inside a box and say, don't touch it inside the box. Only the parts that are outside are your recurring problems of what new surprise is going to come when you plug it in. Today we discovered, for instance, that this particular projector is running on VGA. It is not running on HDMI. And the person who provided it came and set up a cable and went. And later on we noticed and said, hang on, why is it on VGA? VGA is an analog signal. Let's move it to HDMI. We plugged it into HDMI, my capture card crashed. Okay? Why would a capture card crash when you plug in a HDMI cable? Well, so we called the vendor and he said, my HDMI port is not working. So use VGA, please. Okay? But the question is, that's fine, it's not working for whatever reason. But why did that crash when I plug in a cable here? Now, the thing is that I don't know, because I do not have a multimeter to go and see what's happening inside this machine right now. And if I had that particular device with me in my spare time in a lab environment, I will go figure out what's wrong with that port and why is it causing my capture card to crash. But when you come to a meetup and you have a timeline within which you need to run, debugging is not an option. And therefore, requirement of debugging in production is what you want to eliminate first of all. Okay? So a lot of what I've beaten my head over in the past 1 year is just this thing of saying, let's not do debugging. How do we eliminate debugging? How do we minimize all the weird things that happen? And it's not completely done yet. We have found more things that cause us grief today. But let's take a brief journey through some of them. Let's see if I can show you some in some photos. So among the things that I had to do was I wanted to make this work with an ARM chip. It turns out that a Raspberry Pi cannot do the job because the Raspberry Pi 4, while it's an ARM device and has a camera serial interface, has what's called a two-lane interface. And a two-lane CSI interface has only enough bandwidth to do 1920 into 1080 at about 50 frames per second. It can't hit 60. Okay? But if you ask somebody's laptop to give it data at 50 frames per second, chances are it's not going to comply. It says that I don't understand what that is. I can give you 30 or 60. Okay? And then you say, okay, fine, then I'll record it 1920 to 1080 at 30 frames per second because that's all the bandwidth I've got on the camera interface of a Raspberry Pi 4. So you say, okay, fine, let's go to Raspberry Pi 5. That's a new one. And that's got a 4-lane interface, and it's got two interfaces. So while the 4 had 2 ports, one of them was hard-coded to display output, one was hard-coded to camera input. In 5, they're configurable in software. So I can say, I want 2 camera inputs, 4 lanes each, and for the display itself, I will use HDMI, so I don't need to use the, the CSI interface. Great, you think you can do it, and that's basically what I was trying to do down here when I said, yeah, let's use both these interfaces. Well, guess what they changed in Raspberry Pi 5? They removed the GPU. There is no GPU in Raspberry Pi 5. You can only do CPU now. Yeah. Specifically, not the full GPU for the display. They removed the encoder. The video encoder, which is usually part of the GPU package, and it's usually a very low spec, low load part of the package, is gone in Raspberry Pi 5. Okay? And why is it gone? And not exactly. See, so there is some behind the scenes shenanigans, and there is a public statement. And the public statement is our CPU is fast enough, you don't need a hardware encoder. Just do it in software now. Okay? And the second reason being that the encoder that you use, if it's a hardware encoder, it only does a particular protocol. And those protocols change every 5 or 6 years. Every once in a while you come with a better one. So it was MPEG, then it became VP9, it became Modbus, so we've gone through a whole bunch of them. So when you put a protocol in hardware, you're stuck with that protocol for the lifetime of the device. And Raspberry Pi's main promise, the foundation's main promise, is that they will never discontinue a model. They're promising it will be in the market for like 20 or 30 years at least, which means you can afford to do long-term deployments of saying that I picked a particular Raspberry Pi model and I built a product around it, I went to market. 15, 20 years down the line, I can still buy the same model to do hardware repairs. And they're guaranteeing you that they will not discontinue the model. In fact, the only one they've ever discontinued is Raspberry Pi 1. You can still go buy Raspberry Pi 2, which is some 10 or 15 years old, so that's their promise, that we will ensure long-term availability of whatever hardware we put in the market. And if you are going with whatever is a fancy encoder of the last 3 or 4 years and promising that this is the encoder we will support for the next 30 odd years, that encoder is going to be obsolete. And anyway, people will say, ignore the encoder and do it in software because something more efficient is there. And so they said, then why are we doing hardware encoding? Let's dump it, let's go to software encoding. And so he says, that's great for your strategy, but dude, I have a CPU load problem. I can't be doing encoding in software and overloading my CPU. And I can't get enough performance to do 2 camera capture cards running at 60 frames per second, and making sure I have a high enough bit rate. So this was a dead end. So then it becomes, okay, let's go to the other competitors in the space, and that's the Rockchip CPUs. RK3588 is pretty damn good. This one is actually an Intel machine. That's not a Rockchip. It looks like a Raspberry Pi, but it's not. It's a Reduxa X4. I went through the large version, the Reduxa Rock 5 ITX, which is designed to look like a PC motherboard, but it's actually an ARM chip, and it's got a lot of interfaces. In fact, if you zoom in a bit, you can see down here, this is actually a capture card. So they have a capture card built into the motherboard. And then over here, on the side, I don't think you can really see it, but over there, there is cam 1, cam 0. So they have 2 more camera interfaces. Now, this is not a HDMI interface, it's a camera interface. This is a direct raw CSI interface. So you need a HDMI to CSI adapter, which you can get for about 700 rupees. So it's not expensive. So this board looks damn great. It's got a hardware encoder. It can do, I think, VP8 in hardware. It's got 3 interfaces, 1 direct HDMI and 2 CSI interfaces, which means I can plug in a camera or a capture card, whatever. It's flexible, so it's great. Why don't I use this? Well, has anybody done ARM outside of Raspberry Pi? Rockchip? So, you know what this means. I mean, if you have done Rockchip, then you know what driver's situation is like. So if you want all of these interfaces to work, then you're stuck with kernel 5.9, which was released in the year 2019. If you want a modern LTS kernel, which is 6.1, which is also pretty ancient, but it's LTS, it's supported, then your camera interfaces are not supported in that kernel. Okay. Or if you want 6.11 or 12 or whatever is a more recent version, then even more things stop working. And part of the reason being that most of these things, the ARM ecosystem is built around mobile phone companies, which are completely vertically integrated and completely locked down. And among the surprising things, for instance, is that ARM has no concept of a BIOS. So the hardware figures out which boot device to use, directly loads the boot device, and hands it off to software. There is no BIOS to abstract the hardware. There's no hardware abstraction layer that is provided through a BIOS. So what this means is that if it tries to load a kernel that does not know that it is supposed to be on this particular board, it will not even boot. And so you can't download an ISO, burn it on storage, put it on the machine, and boot. It's not going to work. You have to download an ISO which has a kernel specifically compiled for this variant of this board, or it doesn't work. And that means that I can't simply go to any community distribution and say download ISO. Now I have to go to one that specializes in this particular board and say, yes, these people have released one that's working with this board, download it. But what kernel did they compile it with? What drivers did they compile it with? Now I'm stuck with that. And so this is a super fragmented ecosystem where you're constantly looking at niche communities to say that some particular community, some volunteer has bought this exact same board and is interested in the exact same port and has figured out how to compile the driver for it. And therefore you're in luck. And so this kind of becomes half the hassle of doing with ARM. You cannot do this under deadlines. And you cannot do this unless you've decided to become a Linux kernel hacker, whether you like it or not. So for the temporary period, I'm right now using an Intel board. And I wanted this to be as low power as possible, so I tried doing it with an Intel N100. Turns out that on an Intel N100, I can get up to 45 FPS at 1080p. Beyond that, it starts overheating. And so this was one of my other nightmares, that I would have overheating and then it would do CPU throttling, and then to turn off CPU throttling, there's one half you do in software, one half you do in BIOS. And in the process of saying, how do you turn off CPU throttling because you believe it will withstand the temperature? Where do you turn it off to make it persist? Becomes yet another chase. And this became super frustrating. In fact, in the process of trying to make an N100 machine work, I ended up cutting copper by hand and making my own heatsink. And I have some later photos of the process because I don't think I took a photo of that particular moment where I was going through that particular hell. But yes, I have some of these things. Like I went through a lot of hell trying to figure out what is this thing throttling at what temperature does it start throttling? And it turns out to be roughly around 50. So as long as you can stay below that number, you're fine. After that number, you lost your video encoding. So this is the heatsink it actually comes with, this particular machine. And that heatsink has a design flaw. It does not sit on the CPU. And for whatever reason, the company that makes this, Reduxa, left the CPU die exposed, which means if you put a heatsink on it and you say it's not making contact, screw it down a bit more. You're screwing down into the actual die of the CPU because it's unprotected. And a few turns of your screw later, you don't have a CPU anymore, as people have found out and reported online. Okay? And so now this becomes this thing of saying, how much torque can I apply on a heatsink to get the maximum heatsink effect before I've gone too far and I've lost the CPU? Okay? That's not a way to make 10 of these. It's not going to work. So then I end up going up and saying, okay, let's go buy the next available candidate, an N150. This is the one I'm currently using. The brand doesn't matter. I just bought the cheapest I could buy because it was about saying, let's go one step up and see if it works. And it does work. And so, but they've raised the price because Sam Altman has made everybody's prices go up this year. And so it's not worth buying anymore. So this is one half of the mess. The second half of the mess is, how do you get power to this box? Remember, if you're trying to eliminate cable hell, then the first thing is all of these devices need power. So I need a power strip. And if you just go buy a power strip and look inside it, you may not like what you see. Let me show you a power strip inside. This is the nice modular power strip I bought, and it didn't work, and I had to open it and see why is it not working. And can you see it? That thing was soldered when it was shipped. It desoldered itself when I plugged in a device, because it couldn't handle the load, and the soldering was so poorly done that it got hot within a couple of seconds and separated itself. Okay? And so if this is going to happen to you in production, then what the hell are you going to do? So this becomes a quest. Where can I buy a nice power strip? As it turns out, this power strip was half the price. And no such problem here. In fact, those wires are for the LEDs, so it doesn't matter. You can plug those wires off, it'll be fine. Everything here is copper. And so there is no such risk of things coming apart in this particular device. And it cost me half as much, because this is the cheap Chinese import. And that was the Indian one. Okay. So this is a company called MX. In fact, I opened more than one of them. Things to look inside, and I look at it and say, look, man, I will not trust this in production. So one of my side quests ended up making my own power strip, which is what's in there right now. And I can show you my design for it. So I ended up having to go buy individual sockets like this, find different qualities. Some of these come with pins, which have to be crimped. Some which come with screw terminals, where you insert a wire and screw it down. This is much nicer for self-assembly. This is not. This is Indian make, that's Chinese make, cheaper. So let's see. So this is a session I had last year where I invited some folks to come and say, let's figure out how difficult it is to make your own power strip. If you want to make a really high quality one, and one meant to fit in a server rack. Because it turns out that nobody makes a commercial power strip that fits in a 10-inch server rack. You can only buy a 19-inch server rack power strip in this country. You can buy the Chinese version, which is super high quality, but it's not an Indian socket on it. So you can buy a Chinese-made, super high-quality, really cheap power strip, but it'll come with European or American sockets, not with Indian sockets, because that's not a niche market for them that is worth investing in. And so we ended up making these. It turns out that my first design was not very good. You can do this yourself if you want to. All of the specs are right here, including what hardware you need to buy, what it's going to look like when you're done with it, the 3D printed parts that you need to print. So actually, STL is what GitHub will give you a preview for. And basically, it's two components. You know that you have a base like this, and then you have the cover on top of it, which closes it. So this attempt at saying, let's do it ourselves, this is version 1, which is still the one inside here, takes about 2.5 hours to assemble. And the reason it takes that long to assemble is because of the Indian sockets and the weird manner in which you plug wires into them. Yeah, and so this is version 1. I would recommend you don't actually try to bake it yourself. I will come up with a version 2, which is probably easier to implement, but it's the kind of thing that people smile with for photographs with, because it's mission accomplished to make one power strip. So I made 3 of these machines last year. Here are the first 2. This is the very early draft with all cables hanging loose. And right now I have 3 of these in operation and a 4th one, which is just the spare parts in case I need to do repairs. So, and fundamentally it is ridiculously simple. It's just a server rack spec cage. I made a cube so that I can put stuff in from every direction. And all I've done is put a PC and a bunch of capture cards and set them up in a way that you don't have to mess with the wires once they're assembled. The actual assembly process for this rack takes about 20 or 30 minutes, so it's not a big deal. It's something anybody can do. Obviously, I've been trying to work on the next set of problems that come up. And a lot of this is work in progress, pictures of things that I've been trying to do in the process of experimenting, but that's basically the main aspect of it. Okay. If you had to get to talk about the other parts, now about how today's video is working, so since we are here, what's happening over there is that machine is running OBS through a capture card. I was trying to put that machine's own display on the screen, but we'll have to unplug a cable to make that work. So if you want to finish in the next 2 minutes, I'll just show you what's happening on this machine. Okay, so let's. And so what you've got here is now the actual interface on that computer. And you're seeing that computer's desktop. And obviously, because of the way it's set up right now, we're going to start getting parallax. Where is my mouse? Part of the things that start happening is that if you notice my mouse being janky, the reason it is janky is because the receiver for this thing is on the other side of this metal box. And so radio has trouble with metal. And so in this process of learning what kind of headaches you can possibly get, one of the things that I've learned is radio signals are not universal. I mean, our phones have fantastic Bluetooth radios because nobody's going to buy a phone if your Bluetooth headset doesn't work with it, even though the signal has to go through your body. That's not the case when you're buying cheap machines. And so this particular PC has a dinky little radio antenna that is stuck inside the case. And that's not great for signal. So what happens now is that I can't use a Bluetooth keyboard with that PC because it doesn't work in front of the device, because the PC is facing the side of the device. And just that one little bend is too much for that radio antenna to go through. I also have recurring trouble with its display, and like I'll show you an example of sometimes what happens on the display. This is what a Windows login screen is supposed to look like. Oh shit, you can't see it now because now it's not my screen anymore. So yeah, sorry, we'll have to shift the cable over again. And looks like it has decided to stop working now. This is what happens when you touch cables in production. It doesn't want to work anymore. It'll probably work if you unplug something, but we don't know what to unplug to make it work. Okay? And so, in part, what we're trying to do is eliminate this need to touch cables, because your life is miserable because you touched a cable, more than any fancy software or hardware or engineering problem. So that's the main thing. I think we have a deadline to return the projector, so we should ask the projector guy to come and take it. But if you have any questions, I'm happy to answer them. Yeah, out of this talk setup. Right. Thanks, everyone.